Unmute, unmute. I was saying happy Wednesday and I realized we were muted. Hello, hello, everyone. Happy Wednesday once again. Hello, Dominic. How are you?
Hello, thanks. I'm fine.
Good. Welcome back, everyone, to another Create with Maxon with the amazing Dominik Ruckli. And let me very quickly go through the housekeeping because Dominic, as usual, has some amazing stuff to show us. So let me, I need to do this. Or this. There you go. This is the correct one. So use this code. The code I'm going to, the link, not the code, the link I'm going to throw into the chat right now to get to this hub page. There you go. And you can check out the events, the University links, of course, ask your questions, the YouTube channels, and if you want to sign up to get the Maxon. What is this? It's a, what are these called? It's a, oh my God, newsletter? Right, there you go, newsletter. Oh my Lord, I couldn't remember the word newsletter. Of course, go and fill the form if you want to ask questions for the Ask the Trainer session. And if you go to the events, you will see everything that's going on over here, including these fantastic shows by Dominic and myself, of course, just sitting here and saying nonsense. And then you can go to the Maxon Training Team YouTube channel to watch these recorded with timestamps and comments kindly provided by our friend and mentor, Dr. Sassy. Hello, Doctor. And of course, you can go to the Maxon YouTube channel where you can see amazing reels and artist presentations and a lot of other great stuff. And of course, go and learn ZBrush. Please do yourself that favor. And now available on your iPad/couch or bed or wherever you happen to be on the road. Finally, go to University to check out a lot of extremely high quality tutorials. Just go here and type what you want to search for, and an appropriate tutorial will come up. So with that said, let's go over here. There we go. And Dominic, what do you have in store for us today? So let me switch
Thank
your
you,
screen.
Noseman. Yes, yeah, hello everyone. So today we are going again with the Particle Nodes Modifier, but this time we dive a little bit deeper. So we already see it, we go a bit more advanced. So let me go to the next page. Today we are building first an push apart modifier, and in the second part we are building a mesh points attractor. So we just built now just 2 modifiers, but we go a little bit more in depth. So let me show. So the push apart modifier, we will do little setups. So the first setup will be with this super handy node called the point relax node here. And then in the next step, we will build our own point relax. So I will show you some videos then first when we jump in. Then I go into a little explanation. So what we like to do. And in the second part, we are building a mesh points attractor modifier where the particles get attracted by the points of a mesh. So this will look like this. And also here, I will explain a bit so how this works, this concept works. So, and then we will build it. And then if we have some time, I will go deeper and show you some additional examples. Actually here, the main image that we used for the stream is then an advanced version of this mesh point attraction with the shortest path. I will explain this later. And if you have some additional time, we'll go into some other setups here, a group separation modifier, a full tree branching setup. This is just for a little bit of a show off here. This is just if you have some time left, and then also an infection system that I did with the Particle Nodes Modifier. Yeah, but we start here with the first one, and this is this push apart modifier. So let me open some videos for you so you know what we are going to do. So first, it is pretty simple. So we are going to build and push apart. So a modifier where the particles are pushing apart by their radius. So this is what we're going to achieve. And here's a little bit more an advanced version that we can also use colors and of course turbulent fields to build this liquid emotion. We show this again here. So yeah, I think that's it here, and we can jump into Cinema now. So let me close this, then let's go into Cinema. And of course, what do we need first? We need an emitter. We need some particles, of course. Wait, let me open my cheat sheets here if I forget something. But here we have an emitter here. Let's rotate the emitter so we can have a look from above here. Oops, here we go. And then let's make some settings here. Maybe start with 1000 particles. We use shot, and also inside of the properties we don't want speed, so let's check. I think we need more particles here. Oh, 1000 I said. Okay, let's go. And also we want to see the radius of the particles, so because we want to push apart by the radius of the particles. So this you can define here on the particle group. So check draw radius. And now we have a radius of 1, I think. Let's go to a radius of 2. So now we have a radius of 2.
One quick thing, all the files that Dominik is making are available to download. Just go to the description text and you will find a link to a form, and you'll be sent a link to all the files. For anyone that has filled that form, the original link you got by email is valid for all the episodes of this month. So go do yourselves a favor and download the available files. Thank you.
Thank you. So, okay, now let's have a look, and we see we have here overlapping particles. So it would be great to build a system where the particles are pushing apart so they don't overlap. So for this, we of course need here our good old friend, the Particle Nodes Modifier. Put this here under the group, and then let's open it and put it down here. Let's make some space here. Let's zoom in here a bit. And now, as I explained the last time here, inside here, the node graph of the Particle Node Modifier, we are working always one particle after each other. So we have now a problem. The particles don't know where the other particles are. So every particle is as its own. So we need something where we can find the other particle data for each particle. As I in the last stream explained here, we have here those standard properties. And here at the bottom, there is a property called all particle data. And you can see there is not a circle. There is those 4 little squares here. That means we have here an array of data. So what is an array? An array is just a collection with data in it. So when you click on those properties, you can see here the type. So we have here an array collection of the position, unique ID, radius, and you can see this represents here the particle data and the particle properties. So we can decompose this array collection here when we use a decompose container node, then plug this into the container. And
a very quick introduction again is that by the end of the month, I'm already recording some tutorials Some of these tutorials are showing some of the techniques that Dominik is showing, but you're going to have an opportunity at the end of the month and moving forwards to go and see tutorials that talk about a lot of these things for nodes and the Particle Nodes Modifier. Thank you.
Yep, thank you. So, and you can see here, we have now here different arrays. So those 4 little squares here, and you can see these are the same as we have here. So for each particle, we have here the property, and here we have the property data for all particles. So, and what we can do now here with the position, as I explained here, so let's go to this one, we can use here the point relax. So this is a very mighty node. So this is perfect for what we like to do. So let's get the point relax. Here it is. So, and it does what it says. So it relaxes points, and we have here a minimum separation. So it separates all the points that we give here into here by this this minimal separation value. So we can plug in here also geometry, but we like to plug in all our particle positions. So that we have here 1,000 particles. So an array here with vectors. So positions are vectors. So we can plug this in here to the relax points. And then we have here an array with matrices. So a matrice is not just the point position, there's also rotation in there, and also the scaling of the matrix here. Now we have here an relaxed, all the points here, all our particles are relaxed, and by this separation. So the separation we would be great to have here the radius or the scale, so the diameter of our particles. So let's expose this here, press Control and click on this little circle, and then we have here the minimal separation. So we could plug in here the radius into here, but this don't make sense because we are doing this relaxation here. We're doing this for all the particles. And we have here an iteration of 15, so we're doing this 15 times. And if we would plug in this in here, we would do this 15 times. So we have 1,000 particles, so 1,000 times 15. So we need a way to get just the radius of one of our particle. So because they all have the same radius, and we have here an array with all the radius. So we can pick here the radius, for example, of our first particle. You can do this with a get element, and then plug in here our radius into here. And the index is 0, so here this doesn't matter. We take the first particle, and then we have the radius of the first particle, and plug this in here to the minimum separation. Then we have this, how many times we want to relax the points here. So this would be a good idea to have this as a parameter. So let's release it here on the nodes graph, add a new input. Then you can drag it in here. And now we have here the relaxed points. But now we need this information and bring this back to the actual position of the current particle. So we can do this also with a get element. So we can copy this, then plug in here our array of matrices into the get element. And now we need the current particles index. And we have this here. So the current index, plug this in here, bring this to here. And now we can twirl this down. And we can see inside the matrix there is translation. So this is the position, rotation, scale, and shear. So we need just the new relaxed position of our particles. So let's plug this in here. And now let's check what will happen. Let's press play. So nothing has happened. I think the problem is because we're plugging in here the radius, and this minimum separation is actually the diameter. We have to multiply here our radius by 2. So let's use a multiply. Let's multiply our radius by 2. Plug this in here. Let's check again. And now we get a separation, so also kind of a collision of our particles. But we want kind of a 2D effect, so maybe when we rotate around, we can see they also start to stack on top of each other in the y direction. We don't want that. So we could say also in here, to every particle, let's stay at the 0 coordinate in the y position, but we can also do this with another modifier. So there is this handy modifier called the math modifier. Put this in here to our particle group. And here we can say, what's the target property we like to set? We like to set the position, that's correct, but not the X channel. We like to have the Y channel, and we like to add a constant value. So for every particle, the same, and we like to assign it, and the value should be 1. So everything is fine. Let's check again. Yeah, now we have this separation, and you could already see there is a little bit of jittering, so they jitter around. We can prevent this by, of course, adding here to the max iteration, here adding more iterations, but we can also up the substeps of our particle system here. So at the moment, when we go to the project settings, so Control D, when we go to simulation, particles, we have here substeps. So that means that the full particle system will just get triggered once on each frame. So when we say, let's go to 10 substeps, so on every frame we have 10 iteration of our whole particle system here. So maybe let's check this. And now you can see it is much faster, and we also reduce this jittering. So this could be already a solution that is fine, that we need, but we don't want to set here our position of the particles. We like to have here because we call it as a push apart modifier, we like to have this more as kind of a force than of setting the absolute position here. So to build this as kind of a force, it would be great to add here this to our velocity. But for this, we can use the relaxed position that we have here and subtract here our initial position to build a direction vector. And this vector we can use as velocity. So let's do this. Let's use a subtract. So we like to subtract a vector. Then we like to, from the relaxed position, we like to subtract the initial position. And now we have a direction vector that points away from where it has to go. So we can also normalize this. So I think we don't have to normalize here in this example here. We can now use this and scale it first to have kind of a strength, how strong it has to push apart. So this is also that we did in the last stream. Just use a scale. Then let's use the scale. We like to scale a vector. Plug this in here, and this we can use as a parameter. Let's call it strength. Let's also bring this in here. So we have a nice setup here. And then this scaled vector we like to add to our velocity. So our velocity will accelerate over time. So we can use an add. So let's use vectors, use the velocity, add it into here, and then plug this into the velocity here, remove this here at the position part here, and also the strength, let's say 0.1. Now let's check what will happen. Yeah, and you can see it is way too strong now. So we could go slower here, but we can also reduce a little bit of force by a simple friction force. So go to the simulation, force, friction. So now we add a friction, maybe try 1000. Let's press play. And now we can see we have this push apart force that pushes the particle apart. And of course, then you can also plug in, for example, a turbulence. Where is it? It's also on the force. Maybe strength of 5. Go down to the friction, up the scale. Maybe let's reduce the substep so it is a little bit faster. Go to 4 or something. Let's press play again. Yeah, I think the turbulence is way too strong. Just make 1. And then we start to get this kind of fluid feeling. So this is what you can do here with this simple point relax. So, but when we change the radius of our particles, so have different radius, radii is it called, right? Radii, I think. So when we twirl down here on the radius, here under the properties, we can add in some variance, maybe 0.2 or something. Let's press play again. Maybe deactivate the turbulence. And you can see the radius is it don't takes the radius into account here. So this is something the point relax can do, that we can just add one here, one minimal separation here. So it would be great to also take the radius into account. So there, so we have to build this push apart system at our own. But I think before we jump into this, maybe Noseman, let's have a look at the chat. Are there some questions popping up?
Yes. So let me take a quick look here. All right. I've been noodling around, so I haven't checked.
No problem. Yeah.
Okay. First of all, hello to everyone that has come to join us. We have over 100 people watching at this moment. Let's go. I'm not going to say hello to every individual. Why not? Sharon, Mikhail, Phil, Andrea, Adams, Jeremy, Shook Studio, Mikhail. Did I say Mikhail again? I think I did. Dances for Peas, Le Badger. Hello, Badger. Sebastian Wetzel. That's someone we know. The Maxon training team. Oh, wait, that's me. Brian Smith, Dynamic. Ivasenko, Jess, Virtually Visual. Hello, Jess. Who's that? Marco. Hello, Marco. Mr. AE4D. Brian Smith, Eric Silvermail. And in the other chat, Andy, my very good friend, Andy. We're going to try and get you on the show. Let me know if you want to jump on tomorrow. They asked the trainer. You are a trainer, aren't you? Yep. So Weasley, Suzanne, 3 Druid, who else? Agente Laranya, Jonathan Dowler, and Jello Chen, Suzanne Mai. I think that's all. I called everyone out. Fantastic. Now let's look at some of the questions here. Someone was asking, why would we use nodes, right? Why would anyone want to use nodes? Well, it has been replied, but let me sort of add to that. The Cinema 4D is simple. You can use MoGraph to do a lot of stuff. Nodes is just a different way to wrangle data. That's it. You have more free access into the data that comprises Cinema 4D in a similar way that you would use something like Python and so forth, but in a visual way. So it's not replacing anything. It's just an additional thing for people that want to create stuff. Let me give you an example. So Cinema 4D's particle system works with the modifiers, and the system works with the hierarchies and the children of the groups and all that is quite straightforward. And once you get the basic understanding, you can do a lot of things with the current modifiers. By adding the particle node modifier in the mix, now we can do whatever we want, whether Maxon has developed a modifier for something or not. The example is, I think, what Dominik is going to show here is, for whatever reason, we don't have a way to do particle-to-particle collisions. But what Dominik is going to show, or you will see in his files, is that we can make that. Although it won't be as performant as having it built in to work on the GPU, it's still an option when you can't do that. And believe me, even with a few million particles, the particle nodes modifier works very, very decently. The system is very fast. So yeah, it's not replacing anything. It's just an additional thing for anyone that wants to get into more the wrangling of the data. So let's see any other questions. If you have anything to add to this, I'm moving down the list of questions.
Perfect explain.
Thank you. So let's see. Hello, supplemental. Yep. Let's see. Okay, so there's a question here. If I understand it properly, Brian Smith, could you do what you did with the math model have been handled in a node? The answer is yes. There are many things you can do in one single particle node modifier that you would use several other modifiers to do with. So again, it's just an alternative way of doing things. One thing you do need to remember, though, and that's the important thing, all the modifiers work. So modifiers work on the GPU. So all the modifiers we have, which are part of the modifier list, particle modifiers, they work on the GPU. So whatever they're going to do, it happens on the GPU. The data doesn't need to come down to the CPU. The particle nodes modifier requires the data to come down from the GPU to the CPU to be processed and then uploaded again. So you do have this flexibility, but if you're having nearly real-time advection with Pyro with 5 or 10 million particles, doing something with nodes with 5 or 10 million particles is going to be significantly slower. So yes, you can, but the particle node modifier does not work in the GPU. But the way it works is it only downloads the data it requires. So here I'm going to make a little note. You have used, Dominik, the particle data. All the first node on the left is the oh my god, I can't.
Decompose container.
And before that, you're reading all the particle data.
Yes.
I was told that when you do this, it downloads all the data from the GPU to the CPU because you're requesting the whole array. But if instead of getting all the particle data, you use the get particle property node, that using the get particle property node, if you just click C and type get particle, the get particle property or get particle property array, you can tell it to pick only one of the arrays you required. And that way it makes the time to access that data from GPU to CPU much faster because it's requesting less data. I think that's how it works. If any of our developers is in the chat, let us know if you do have time, if
Sure.
it does go faster.
Great. Yeah, that's a good tip. Yeah.
Yeah. Hopefully it's true. I mean, it's a good tip if it's true. So
it looks like it works. Yeah. So I plugged in here the get particle property array and typed in position.
Yeah, it works with a single. The question is, does it work faster because it requests less particles? So
Yes.
increase the particle count to a few million, and we can see. Okay, let's see what this question. So I have another question here by Trex, PIBX Trex. Is now it's similar to Grasshopper inside Rhino? Can we use geometry and math nodes? I haven't used Grasshopper. I've heard of it. I haven't used it. And Rhino has only come across my desk a couple of times for different reasons. But all nodes systems have similarities. Now, having said that, Cinema 4D's scene nodes was designed to work with geometry and then extended to work with particles. So the answer is yes. And part of the tutorials we're planning for the next couple of months includes how to deal with geometry. So that's okay. How would I go about making emissive particles using this rig? Emissive, you mean using Redshift with emission, or to reproduce particles? I think you mean the former. Yeah, you can. It's not difficult to associate to create an extra custom attribute. For anyone that missed the memo, 2025.1 introduced custom particle attributes, which means that you can set a secondary color attribute, which you can use into Redshift to control things like emission and all sorts of other things. And yep, let's see. Andy, position. Yes, the if you use the get particle property or particle property array, make sure you go to that drop down and type the property as it is. It's case sensitive, so position with a capital P,
Yes.
alignment the capital A, and so forth. And yes, using Redshift with emission. And it's as I said, so you would go and create a custom property. And in that custom property, you're going to set it to RGBA, and you're going to give it a name, my emission, and you're going to read it in Redshift. There may be examples for those in the parts of the tutorials I'm making. There's a lot of stuff to do. And maybe, why don't you join us tomorrow? I'm going to show you tomorrow how to do it in the Ask the Trainer. Excellent. So I'm going to hand it back to Dominik. Please continue. Thank you very much.
Yes, thank you. So let's jump back to the presentation. So as I already explained, with the point relax, this is a cool, simple method. So we can relax the particles here by their radius, but they all have to have the same radius. So, but we can do this at our own. So let's go further here. So we can do this point relaxing at our own. So now it gets a bit techy, but I hope you can follow along. So everybody that knows me from my tutorial, I always try to explain stuff as good as I can. So, and then we can build step by step. This was also a question that popped up last time. So how to approach stuff like this. So it is always good to break down stuff down step by step. That is what we are doing here now. So let's have a look here on this slide here. So let's assume here we have 3 particles here. They have different radii and they are overlapping. So, and now we need some data to build our own push apart setup. So first thing we need, so we assume we are running over this particle. So this is our current particle. So what we need first is we need the neighbors. So all particles that are in a certain distance. So then these particles here, so here in this purple here. Then what we need next is the direction to the neighboring particle. I call this here normalized direction. So a normalized direction is that the vector here always has the length of 1. Then what we also need here is the distance to the neighboring particles. And then in the next step, we also need to know the maximum distance. So when we think of this smaller particle, when this is there where those dotted lines are, then they are aligning perfect. So that means when this particle is here at this maximum distance, it don't have to go, we don't have to push it further. So the maximum distance then of course is the radius of the small one and here of our current. So radius plus radius gives us the maximum distance. And then the next step, we need the difference, so the distance difference of the current distance that we have of the overlapping particles and of the maximum distance. So this is here, this blue line. So we take the maximum distance, subtract the current distance, and then we have this leftover here. So this is the difference. And this difference, when we go to the next slide, this difference we use to scale our normalized direction here So this is the normalized direction here, this transparent arrow here, and then we scale it. So we multiply it by the difference here. Then we get this smaller vector. And then when we have all those scaled down vectors, we collect them and we build an average direction. I showed this here with this orange arrow here. Then we have to flip it. And this direction now, this average direction, will be our velocity. When we add this velocity here to our current particle, you can see the particle moves away from the other particles. So that's what we have to do now. So we will go back into the presentation so I can explain. So we build this now step by step. So let's jump into Cinema. Here we go. So let's deactivate this one. We built this from scratch. So we build a new one. Let's go to the modifiers here and add a Particle Nodes Modifier. Maybe let's call this push apart, like say custom, something like this. This is here our advanced push apart modifier. So, and what do we need first? So we need the neighbors. So as I already explained, the particles inside here, they don't know nothing about the other particles. So we need a node to find the closest particles around our current particle. So and there is a very handy node. That's one of my favorites. This is called the closest points. So, and yeah, of course, it does what it says. So it searches the closest point of a current position. So the query position, so the current position is the position of our current particle. So let's plug this in here to the query position. And then we have here the geometry to search the closest point. So we could also plug in here geometry, but we can also plug in here a set of points, so an array of points. So let's get here all our particle data, so the data of all the particles. Let's use again the decompose the container, and now we have here all the positions of all our 1000 particles that we have here in our system, and we can plug this here into the geometry. Then let's have a look here at the settings. There is a selection string, so if you work with geometry, you can define a selection, but we work with just points, so this is useless here. Then we have a maximum distance to search, so 100 centimeter I think is fine for this setup. And then how many neighbors we like to find. So I think one is not enough, so we can definitely define, this via a parameter. So let's bring this out here, this in here, and go to our modifier here and say, maybe let's search for 8 neighbors. And what we have here now, the output of the closest point, you already can see it is the nearest indices. So now we have here the index or the indices of all our neighboring particles. Just maybe let's press play and let's zoom in. So maybe for this particle, it finds this, and this one. So we have the indices, so the index of each neighbor particle. So great. So we have here our neighbors. Next step, what do we need is the normalized direction and the distance. So we need not just the neighbor indice, we also need the neighbor position. So let's dive in. Now, because we have here an array of 8 neighbors, we have to iterate over those neighbors. So there is a very handy concept inside C nodes where we can iterate over an array and do an operation and collect this data at the end. So let's use an iterate collection, plug in here our indice array, and here you can see this iterate collection has this curly bracket little icon here. So that means we are open now in collection. So we iterating over our 8 neighboring indices, and here under element we have the indice of our neighbors. And with this indice, we can grab the position of our neighbors. So let's use a get element. So plug in here our positions, and then let's say put the elements, so the indice of our neighbors into the index, and now we have here the positions, and now again we have to build a direction, so we can do this with a subtract. So data type is vector. So, and we could subtract the neighbor position from our current position. So, but as I explained here, we need the flipped direction. We can already do this here. So let's switch those. And now we have already the flip direction, the direction that points in the other direction. And now we have here all the directions, and those directions we have to normalize as I explained here. So we need the normalized direction. We can do this with a normalized node. So plug this in here, and now all our direction have the length of 1. So maybe let's make this also this pinkish, so it has the same color as in the in the explanation slides. And then we also need the distance, so the distance from one particle, from our current particle to the neighbors. So there is a node called distance. We could do this with this one. So you plug in 2 vectors, and then you get the distance. But because we already have here our direction, which can just measure, so the direction is actually this green arrow, so we can just measure the length of this vector. So let's type in length, and then we have here the vector length. Then let's measure here our direction, and this is then our distance. Maybe let's call this distance and make it also green. Great. So what do we need next? Let's go back here. So we need the maximum distance. So this is, as I explained, the radius plus the radius. So let's go back. So we have here the radius of our current particle, and we also need the radius of here our neighboring particle. So also let's use a get element, and here are all the radii of all the particles. Plug this in here. Also the elements into index, and now we have here all the radius the radii of all our neighboring particles here. Then let's add them together. Let's use the radius of our current particle and the radius of our neighboring particles, and now we have here the max distance. Maybe what was the color? It was kind of yellowish orange. Okay, something like this. Great. So what was next? We need the distance difference. So we have to subtract the current distance by the maximum distance. Let's use a subtract. Then from the maximum distance, the current distance, and this was blue in the slides. So here we go, and now we have here this difference. Maybe call this. It's great. Then let's go back. So what do we need next? Now we need the normalized direction we already have. We have to multiply or scale it by the difference here. So let's take here, this is here, our normalized direction. Let's use a scale. So we like to scale a vector. So our normalized direction, and scale it here by the length here of our difference here. And now we have here our scaled direction vectors here. And now, because we need an average direction of all our scaled directions here, we have to collect them and then build an average. And this is the end of here our iterations, because we started here an iteration over all our 8 neighbors. So we have here now the scaled directions of all our 8 neighbors. We have to collect them now. So we have to close this loop here. So we can do this with it's called assemble collection. So we like to assemble everything that's inside this iteration here. You can see we have here also this curly bracket. So that means here the iteration stops. So it ends here. So we can plug this in here. So now we are closing this iteration and collecting here the values. But of course, we have to specify here the data type. There are different ways to do this. The easiest way is just to expose the data type. And we know we want to collect vectors. So when we want to build here an array of vectors, so a collection of vectors. So we could use here, for example, this position, that this is already an array with vectors, plug this into the data type, and then it generates here this type of, we can delete this now, and now the assemble collection is set. You can see here the data type, you can also throw this down, it is an array with vectors inside. This is the easiest way to set this data type. Of course, you could also go in here and set it in here or down here if you need a special custom data type. But that's it. And then we can collect here all our scaled directions. And now we have here again an array with all our neighboring, with the 8 directions of our neighboring points. And
can I jump in for a second? Just want to say what Dominik is showing now, closing the loops and all that, those are standard things which you learn once. Dominik is showing it in an active, he's in real time building an asset right now. Okay. It's the equivalent of watching a developer writing a plugin in real time while you're watching it live, right? This is not recorded, it's live, unless you're watching it recorded, which makes it a recording of a live. Oh, sorry. So the idea being that although it may appear confusing because we got 9 or 10 nodes in there and we're trying to do certain things, there are certain rules that apply to the difference between arrays and iterations and single variables and then compilations of variables and all that. It's a number of rules which once you learn, you can use across the board. The one thing I want to say is that scene nodes is literally a visual programming language. So it has more, let's say, programmatic concepts available to you than other node systems. And that's why it has this extra bit of complexity, because there's certain things you can do that go deeper into the system rather than just on the surface. So if you do get confused with all these things, don't worry. There is a plan for tutorials exactly about these things. That's what I wanted to say. Thank you very much. You can continue.
Mm-hmm. Yeah, that was very well explained. It is, as you said, it sometimes it looks a bit complex, and I also want to try to explain it as good as I can, so as also take you a little bit of the fear of this stuff. So it could, if you get the basic concepts of, as you said, it is a little bit of a visual programming. It starts to make a lot of fun if you get the idea. And this is the similar thing that when you learn a programming language, or you're learning geometry nodes, or you learn vex and wops inside Houdini, you have to understand this basic concept of programming. So, but if you get this, as I explained last time, also when you want to learn how to texture, you also need to know all about surfaces, how surface refract and reflect. And this is a bit the same. So, but now let's go further. We are close to the finish line here. So, as I said, we have here now all our neighboring, from the neighboring particles here, we have here the directions here. So now here in the presentation, we need this average direction. So this we can do with a node called Arithmetic. You can just type in average, and there it is. Arithmetic, and the operation type here is average, and the data type is vector. So, and now we get here, we can plug in, you can see here we have an array that we can plug in here, and now we get the average direction of all our directions. So great. And this is, as I explained here, our final velocity. And we like to build a force, not to set an absolute velocity. So the same procedure as always. Let's scale it first. So we have here a strength. So we can define here our strength. Let's call it strength. And let's set the strength to maybe 0.1. And then here our final velocity vector, let's add this to the initial velocity. Let's add. Oops, here we go. Let's set the type to vector. So take the velocity and add it in here to the, here this together. So, and then to the velocity output. Now fingers crossed, hopefully everything works. Let's check. Yeah, we can already, let's make some frames here. We can see something is happening. So, but we have here one problem. They start also, instead of just pushing apart, they also start to clump together. This is because when I go back here to the explanation, because when we subtract, if we're subtracting here from the maximum distance, here our current distance. So, but when one particle is further away here, so example, this one is further away, then the current distance is bigger than our maximum distance. So we get here a distance, so we get a negative value. So, and with this, we are building a negative force. So we don't want that. So we have to clamp here our value first. So here our difference here. Let's check here. Yes. Our difference, we have to clamp it so it don't goes into a negative value. So let's use a clamp. So plug in here our difference, and we like to clamp it between 0 so it don't goes into negative, and the maximum is our maximum distance. Plug this in here. Now let's check again. Yeah, and now we can see they start to separate. You have to give it a little bit of time, but now it acts as like a fluid. And here is the same. You can, if you want to make this faster, you can first add more neighbors, but I think 8, 10 is good for now. Whoops. Sorry. Oh, I deleted it. Go back. Here we go. Add some more strength, maybe 0.3, and then also raise the substeps that we did in the example before. So let's go to the settings, maybe add 10 substeps. Let's check. Whoops. Oh, I have to add neighbors again. Here we go. And now we get this push force that pushes the particle apart. And just to round this up, let me show the final setup that I built to that I showed here in the start image. This one. So let me open this. This is here. Okay, let's check. And here you can see I also added some colors, also some turbulence, and also a lot of substeps here to have a nice separation here. And people that watch the last stream, they will maybe recognize here we also using here the our own field turbulence modifier that we built in the last stream to get this nice swirly motion. And I think also here the sample image. So I'm sampling here an image, also this leaf image that we used in the last stream. And I plugged I used the green value of this image to change the radius. So I have here some settings to change the radius, and then you get stuff like this. Yeah, I think that's it for this part. And then I think we can have a look into the chat. Are there questions?
Yeah, there's amazing stuff. One thing I want to mention, so I think you mentioned it last week, but it's very important. One of the great advantages of C nodes is that whatever you make, you can encapsulate it and make your own tool. So you can take this push apart, you build it once, or someone builds it for you, you make it into a group, then you make it into an asset, and you can use it just like you use any other tool in Cinema 4D. You can have it in your asset browser, you can share it. If you update it, you can version it. So it's the new version. So your older files open with the older one, the newer files with the new one. Just like if you check out all the capsules that Rocket Lasso has made, that's how they're built. They're built using nodes, and they're encapsulated as a tool, and they look indistinguishable from the other tools of Cinema 4D. So you don't have to repeat this again and again and again, providing you make it in a way that is a bit more, has a bit more control, and you expose the settings properly and all that. Now, I do want to answer a question that was asked by Lisa. Hello, Lisa. To get a foundation of nodes, will you recommend to start with C nodes, texture nodes, or other? My reply would be, well, since Redshift is fundamentally based on nodes, then you start with Redshift, because that's what you'll have to use. You don't have an alternative for that. But in terms of using Cinema 4D in general, especially if you're now beginning your journey into 3D motion design and all that, nodes is a much more advanced thing. Everything you have seen made in production by Cinema 4D artists and studios up until, I would say, yesterday, has been made, with the exception of Dominik's stuff and a few others that use nodes, have been made without the use of scene nodes. So don't forget, Cinema 4D is an amazingly powerful and easy to use software, which can do great stuff. And until you have learned how to use the classic tools, believe me, the need for doing production using the node system is very, very small. You will know when you're going to need it, but it's going to be after you master all the other tools of Cinema 4D. And hopefully with, if you do want to learn C nodes, despite that, make sure that you catch up with all the tutorials. And in one of our chats, we have someone called C nodes tips. I have a suspicion of who that is, but there are, besides Dominik's tutorials, there are other tutorials out there. Let me see if I can. People have been making tutorials. I think there's a YouTube channel called C Nodes Tips. Do you have any information on that?
Yeah, there is one. It is called C Nodes Tips from I think
Donovan?
from Donovan Keefe. Yeah,
I think it's Donovan.
Yeah, it is. I know.
Okay, let me post a link.
Shout out here to Donovan. I learned a lot from him. And this channel, I also can recommend the channel for beginners nodes, the channel of Core4D. So they have also a complete beginner series on their YouTube channel. So they start super basic, explaining all the nodes, all the data types and stuff. So if you want to start C nodes, then this is also a good place to start. Yes.
Yeah. So nodes is a great tool, which will be part of your tool chest, but you have tons of other tools that come before that and have been developed over many, many, many decades. So if you want to achieve a certain thing, that's when you can ask your questions on Ask the Trainer and all sorts of other places. So make sure you ask about what you're trying to do, and if nodes is a solution, then that will be it. There's Dominik's information over there.
You can also at my Instagram channel, if you like, can contact me on Instagram, or of course on YouTube, right into the comments, or you also find there my email on YouTube. So if you have a question, just write me email. I'm happy to help you.
Good. So enough with the chit chat. What else are you going to show us, Dominik?
I already saw we are 1 hour in, so I have this additional concept here. So called, where is it? Called the mesh point attractor. I hope the people in the chat are not too exhausted now. So
no. They're going to stick around, and they love it. Yeah.
Maybe I up the pace a bit, so I hope you can follow along. But I will also go here. We'll show you some videos first, what we're going to build. So that will make sense for you. So as I said here, it is called the mesh points attractor. And let's search for some videos. So this here is the setup, and you can see the particles are searching the closest point on a mesh surface. And when they reach a certain distance, they look at the neighbors of the mesh points of the current attractor point and switch to the next one. And then we start to get this kind of wireframe like hot display like look. I have also some other example here with our good old elephant. So let's open it. Come on, yeah. I also added a tracer to the particles to build those to run around the wireframe of the elephant here. It's also a cool look. And then maybe a lot of you already ask, hey, why does he show us this this main image of my presentation? So here is the actual animation of it. So this is the same concept. So the particles are searching the closest point on a mesh, but instead of choosing a random neighbor to go next, they are searching the closest. Oh, maybe let's just open this for itself. So they search the closest neighbor on the mesh, by which the closest is to, here in this example, to this ball here in the center, and then you get this this kind of vein-like structures here. And some people that watch my tutorials, they know I built this also in C nodes. This, come on, yes. With this, you can build this tree-like structure. So this is an algorithm called the shortest path. So you can also go onto my YouTube channel and watch this tutorial to see how this actually shortest path will work. So if you are totally interested, go in there and you can build then like this setup with what we are doing now. So we don't want to go into this depth, but we want to build, let's open this video again. We're going to build this puppy here, where it chooses a random point, the random neighbor point, and then it starts to slide around the surface of our mesh. So then I would say I have here a little explanation. Hope everything is not too bored about this stuff, but I think it's important to understand the concept behind it. So we have here a mesh with 9 points here, so super simplified. And then we have here the emitter. So we're looking from the side, we're looking in kind of a 2D view, and then we emit like here 3 particles. And those newborn particles, when they get born, so they have first, what they have to do is to search the closest, I call this here attractor point of the mesh. So for this particle is 1, for this 2, for this 3. And out of the position of the particle and the position of the mesh point here, we build again a normalized direction, and this will be our velocity. So the particle knows where to fly, so it flies to its attractor point here. In the next step, we are checking the distance of the particle to its current attractor point. So, and if it reaches a certain distance, so we can define this distance, we start to ask, make an if statement, and then we ask, is it lower than this distance? And if it is lower, what we are doing then is we have to search first the neighbor points. So from this point, we have to search the neighbor points. So for point 2, it is 1, 5, and 3. Then we have to select one of those neighbors randomly. So we like to select the random neighbor. And then we have to update our attractor point. But for the moment here, the attractor point is 2. And then we pick a random neighbor, update our attractor point, and our new attractor point here in this example will be the point 1. So now the direction here will change. So now the particle goes in this direction, and then of course so on. So that's the effect where the particles start to slide from over the mesh from mesh point to mesh point. So, okay, then I think let's jump into it, into Cinema here. So what's going on, Cinema? Hello? Oops. Here we go. Okay. Is it crashed? It is crashed. Sorry. Maybe because
Oops.
Played in the background, and I was too much. Maybe let's restart it again. But,
What happened? It's
I don't know. Maybe
let me share my screen while Dominik is doing stuff. I'm doing the same stuff.
Great.
And here's one thing. When you're ready to go, let me know. So here's one thing I've been working. So everyone now is getting a sneak peek on the tutorials that are upcoming. So basically, this is a tutorial that just shows you very simply how you would go, and the particles would actually go to the mesh points, just like this. So the additional thing is just a noise. And the way you would do something like this, it can change based on the geometry. So depending on how many points I have here, you can see they're always going to the points you need. Everything you see now is playing live. Make it smaller, you can make it bigger. And what's great about this setup is that it's extremely simple. So you get your geometry points, you get each point of the geometry, you do that subtraction to create a force towards each and every one of the points, and then you control the velocity, and that's it. You mix it. And the reason I have the mix is that I can actually put a field in here and mix what's happening. Anyway, that will give you an idea of how the stuff that Dominik is making. You will have a comprehensive guide into these. Here's a geometry component of it, and you can actually make it into a group. So you can name this weird group that gets the points. Okay, that's a group that gets points. There you go. That's it. You can change the icons, you can change the names, you can do whatever you want. And next time you need this, you just copy and paste it in your scene, or you save it as an asset. Then subtract. You can call this go towards and whatnot. You can make another group out of this. So suddenly, once you start naming these Noseman-s, amazing, I would say node, but I'm going to say nosed, right? From now on, that's the terminology. It's a nosed. So you can actually create 2 of these, and next time you want to do something like this with a different object, you can say, well, I have my tool ready. All right, and that's a great thing about it. Anyway, that was just a sneak peek into the stuff I will be doing, and now I'm going to switch back to Dominik's screen. Did I do a good diversion here?
Very good. Nice. That was perfect. So thanks. So I'm back here. Cinema is up again here. So what we need first, of course, we need again an emitter. So let's bring in here a basic emitter. Here we go. And then we need a mesh. So we're building the mesh points attractor. Let's keep it simple. Let's use a sphere. Maybe go to icosahedron. Let's reduce it, something like this. Then let's bring this back a bit. Let's maybe add 1,000 particles. Oops. Make them bigger so you can see it better here. Let's press play. Great. Then we need where is it? Our Particle Nodes Modifier. Add this to the particle group, open it, then go into here. Let's bring up my cheat sheet. Great. And so let's go back to the presentation to see what we have to do. Oops.
A piece of advice to everyone: never ever have a cheat sheet on your main screen.
Yeah,
I can't function without a cheat sheet, and I advise everyone to cheat. Just write notes everywhere. Just stick notes everywhere.
Okay, so we need first, of course, we need to search for the first attractor point. So, and this we need to do when the particle the particle are borning. So it's just this time when they are on the first frame, when they get born, then we have to search for the attractor point. And if the attractor point is found, we have to set this attractor point. So that's the thing we do first. So every particle needs an attractor point. So we can define this with our own custom property. So let's go into our settings here. To particles, let's add a property, and maybe let's call this attractor. And because we are searching the indices here on our mesh, we can choose here index, and now we have here our custom property called attractor. And we also need the information when a particle gets born. So let's go to the basic emitter. Then under output here, we see we have this custom property. It's called born. So the basic emitter knows when our particle gets born. So we can also go to the custom properties and add another one. Let's call this born. So we could use here a Boolean value because the born state could be true or false, but it is actually it works with the Boolean, but it is, to keep it proper here, so it is actually also an integer value. And then you have here this little auto checkbox. So because normally when we build custom properties, we are the only person that can manipulate those values here inside. So we have to allow our emitter here. We have to allow the emitter to override our custom defined properties. So, and that's why we have to check here this auto, and now we are allowing here the basic emitter to override this our custom property called born here. Then let's go to the emitter, then use the born here, then bring them into our setup. So let's say get property. So let's get the property. This will be born. This is the attract. Let's say, okay, the mode is the current. From the current particle, we like to have the born property. And this is an integer. And also the attract. Let's copy it here so it's a little bit faster. Bring this in here. Also integer. Then we can check now here our property by just plugging into the radius. And now when you right click here on the property value, open the data inspector, and let's go a frame forward. And now we can see we have here 40 particles. And all those particles have here the born value of 1. So maybe let's go a frame forward. And now we can see, okay, the particle from before, they have now the value of 2, and the newborn particles have the value of 1. So that's what we can use to say when a particle gets born, when not. So for this, we can use a condition. So there's a node called compare. So we use a compare, and then we have here the operation type. So first, what do we like to compare? We like to compare here our born value. The data type of the born value is an integer, and we like to check if it is the born value equals to 1. So that means if it is equals to 1, the particle gets born. So then we have here a value. It's a Boolean value where it says, okay, if it is true, the particle is newly spawned, and if it is not true, the particle already exists. So great, we can use this to search for our initial attractor point. So let's go back. So now we have to search for our attractor point. So this is the same as we did in the example before. We can use the closest point for this. Here is the closest points, and the query position is the position, of course, of our particle. And then we also need the geometry of our sphere. So at the moment, the particle points modifier has no idea about the sphere, so we have to import also the sphere. You can do this by an object link. So here is an object link, and now this is an input. You have this here, you can also have it here. So when you delete this, you can also always bring this back to have the parameter in here. So then go to the Particle Nodes Modifier. Now we have here a link field. So perfect. Here we can add our sphere. Then we have here our plane geometry, the matrix, the color, and so on. And because we shifted the sphere a bit, we also have to shift here our initial geometry. This here is just a plane geometry. So we have to shift this by our matrix. So this is a procedure that when you work in nodes, you normally do at the start when you import geometry. So use a transform geometry. Then let's transform the geometry by the matrix here, and then we'll plug this into the closest point. Go to the closest point. Now we could use here selection string. So if you wanted to find just the points that are selected and the maximum distance, maybe let's like 10,000. So it is also works in bigger setups. And we like to search the first attractor point. So we just have to search for one neighbor. So that's fine. Okay, and then we have here again the array of the nearest indices, but because there's just one indice inside, we can get this, get element. So the index is 1, and now we have here the index for every particle of the closest point here on this surface. So, and now we have to set here our attractor point. So let's use a set property. And again here, let's copy here the parameter. Let's set this. And this is also an integer. And we could plug this straight into here. So, but now it would set the search for, on every frame, it would search for the closest point. We just have to do this once. So that's why we have here this, this condition. So we can use an if statement for this and add in here our condition. And now, because we have here a value for a Boolean value that is true or false, so we can say if the particle is born, so then it is true, then get here our initial attractor point. We also have to switch it here to integer, the data type. And if the particle already exists, so then it is false, we can get here our current attractor point and plug this into here. So yeah, this is maybe already a lot, but we are close to see something because now we have the attractor point. We know this information for every particle, and now we can build this normalized direction. So let's, because you have here the indices, we have to get the current here on the geometry, get the current position. So we can say get position, and then there is this handy node called geometry property get. So we like to get the property from a geometry, and we like to get the position. So let's plug in here our geometry, and then we have here again an array with vectors, so an array with all the point position of our sphere here. So then let's use and get the element. We like to get the position, and we like to get here our current attractor point. And then to build the direction, again, same procedure. We like to subtract. Oops. So let's subtract here our the position of our attractor point with the position of our particle. Then again scale it. Maybe let's make also a parameter again, as always, strength. So we can control this outside of the nodes graph. Let's set this to maybe 30. Then we plug this in as an absolute velocity. So we override the velocity. And now finally we can check. Oops, I think this is something went wrong here. So this is way too strong. Yeah, it was just way too strong. Let's add some additional frames. Yeah, and now you can see they start to reach here the closest point. Of course, they get stuck here because we have to go further here in our explanation. So on to the next slide. Now we have to check the distance here. So how can we do this? So let's go back here. Oops. Now, because we have here this one, sorry, we have here our direction. So we can again measure this direction. So we know the distance. So let's do this again, as in the example before, called length. We like to have the vector length. And now we have the length of the vector. And this we can also use a compare, as we did here, to check if the particle is close enough to our attractor point. So maybe we can copy this here. Let's switch it to float, because we have here the distance. This is a float value. Plug this in here. And then let's say if it is less than a certain distance, so this one we can define from outside. Say min distance, for example, is in here. And then let's say if the particle is in distance of maybe 5 centimeters, then we have to search for the neighbor points here. We are close to the finish here. So are there some questions again before I do the last part here, or should I just work?
Yeah, very quickly, before you go on, this is a special thing for Brink 3D. is it LDN or IDN, whatever. So is this what you want? To emit from a source, do something, and then go to a destination? If this is what you want, unfortunately, we can't do it. See, that's a joke. Of course we can do it. And yeah, it's a fairly simple setup. But yeah, we can emit from sources. There was a question by Marco that says emit from an object or emit. No. So what you need to do if you want to emit objects is first of all, go and watch all the particle tutorials on Cineversity. And very quickly, when you have any kind of emitter, you create a MoGraph clone or a matrix. If you put it in a cloner, you can add any object you want, set it to objects, and drag the particle group in here. And now each particle is going to become a matrix. There you go. So that's how you do it. And yes to everything. I'm handing it back to you, Dominik.
Okay, then let's do like we're close to the finish line. So let's jump back. So we have to build now this if statement. So we are now have this condition here. So this condition defines if the particle is in the certain range to our attractor point. So let's build this if statement where we can now search for a new neighbor point, search for a new random neighbor point. So let's make some space here. I forgot here a little thing here. We have to, as I said here, we have to build normalized, a normalized direction again. So that's because they are going to be slower and slower. So just do this here, normalize. So we have a constant velocity. Just let's check. Yeah, and now it is way too slow. Let's go to 30. And oops, that's the wrong one. Sorry. This one here, let's go to 40. And now we have here a constant velocity. Great. So let's bring in here our if statement again. So bring in the condition. And if the condition is false, so if the particle is not in certain distance of the attractor point here, we can keep our current attractor point. So we can plug this in here. So also the type is integer. So the indices are integers. And now, but if it is true here, so if our particle is reaching a certain distance, we have to search for a new neighbor point. So there is also a very handy node called neighbor, geometry neighbors. And this one we can search for neighboring points in the geometry. So let's use our mesh geometry here. And then the index is the, of course, from which point you have to search is the attractor point. So here our attractor point here, plug this in here. And now we get the indices here of our neighboring points of the attractor point. So in the example here, like those 3 points. And now we have to select a random neighbor. So for doing, to build a random number, there is a node called hash. This is also a super handy node. And you can already see you have here 2 seed values, so a seed and salt. You can define a minimum and maximum, so the range of the random value. And then you have for every data type, you have an output. We need a random integer, so a random neighbor index. So we have to define first the maximum. So the maximum is also the how many neighbors do we have. So we need to check here first how many neighbors do we have. So let's use an get count. So now we know how many neighbors there are for our attractor point. So we can plug this into the maximum. And then we have here an integer, so a random value between 0 and the maximum of our neighbors. And with this integer, we can pick here one of our new neighbors. So let's use and get element. Plug this in here. Then let's use here our random value. And now we have here a random neighbor. And we go back here to this if statement and say, if we reach a certain distance, we plug in here our new neighbor. So, and now let's check. Maybe let's show it here as lines. Here we go. And you can see we have one problem. They all go in kind of the same direction. This is because here on the hash, we have the seed and salt. So that means every particle has at the end here the same integer. So this makes no sense. So we need to make here a random seed and salt for every particle on every frame. This is pretty easy. We can use the unique ID because every particle has a unique ID for the seed here. So maybe bring this down here. And then because you also want this on every frame, we can use the age of the particle. This is here. Bring this down here also. Then let's check again. And here we go. And now they start to slide here over our mesh surface. Yeah, I think that's it. And then, of course, you can color it. You can play here with the settings. Maybe when you up the minimum distance here to 10, they start to change direction much earlier. So maybe let's check this. Yeah. Get a bigger distribution, or you can also go super low here and then you get those sharp turns of the particles, for example. Oh, I think this is too sharp, huh? No. Okay, let's go to 1. Yes. And then, of course, add color and stuff. And you could also build, just for the last step, you could build an, instead of set an absolute velocity, we could also build this as kind of a force. So let's add here our newly created velocity here to our initial velocity. Then of course the strength has to be very low. Maybe let's check this. Oh, I did something wrong. Add this to the velocity. Okay, I think this one is this too fast here for, yeah, gotcha. I think so, to reach the, no. I'm not 100% sure why this don't work. So we could try to get add some friction to remove some energy. Maybe this will help. This is way too much. Yeah, now it starts to work. So now we have, it's not an absolute velocity, we have now a kind of a force, and it looks, yeah, we also have a different effect. Yeah. For just to show you the last setup, I can show you the file here, what I did to, and then we can round the stream up, I think, just to show what I did here in the with the shortest path solution. So this is the same setup here, but instead of picking a random neighbor, I pick the neighbor that is closest here to our center point. So you get these structures here. So let's pick here our attractor here. You can slide around, and they will always search the closest neighboring point to here our attractor here. So yeah, this is the difference to the setup that we built to get these veins-like structures. And yeah, and I think that's it for my examples. So yeah, I think we're already definitely over time. Huh? So yeah. But maybe there's just last round of questions, and then we can round this up.
It's mostly compliments. So
Cool, thank you.
yeah, so I would like to respond. So let's put our beautiful faces up here, respond to a few. So C nodes are insane. Any series to help beginners get the hang of it? No. Right, don't. Let's let me guide you through this. All right. C nodes are a great tool to do a lot of great stuff. If you are a seasoned Cinema 4D user and you understand data types and data structures and stuff like that, the tutorials that we are going to be making over the next few months are going to be a good guide into getting into nodes. Because, and the reason is, there is a lot of overhead in terms of learning structures, arrays, containers, synchronization, elements, and all that kind of stuff, matrices, vectors, and all that. If that is stuff you comprehend already, then the methodology will be presented in tutorials. But there's so much overhead in terms of knowledge that has to do with nodes, with nodes in general, when it comes to the to wrangling the data, which makes it an extremely high, let's say, bar for us to cross. It's extremely difficult because we will need to make an enormous amount of tutorials for that. What the hope is that by enticing more people, geniuses like Dominik and others that are using the technology to do more content. And so our focus for the time being is for people that are more than intermediate advanced level. So they only learn the specific C nodes techniques, but they already understand the data, the structures, and all that that stuff. So I know it's not what you wanted to hear, but it's just reality. There's too much information to be done. Eventually and ideally, we would love everyone that does 3D to use Cinema 4D and us to be the people teaching everyone how to do all this stuff. But for the short term, it's mostly how to use nodes. And if you have the time and the energy to go and learn all the underlying fundamentals, we're always going to be here to answer your questions and help you through that. But you do need third-party resources. You need to read, watch other tutorials. I would say go watch tutorials about how other people are using other node systems in other softwares, and then you can take these techniques and translate them into Cinema 4D nodes. But the most important thing, and sorry for saying so much, make sure you know Cinema 4D standard tools, because there's a question here that says, can you use it to create? Let's see, where is that? Where was that question? About a landscape or some sort of with a spline, make roadways using a spline. You can do that using fields. So my suggestion is learn how to do things with the standard Cinema 4D tools. And if you get to the limit of what Cinema 4D can do, then go to the next level. If you do have questions on how to do certain things, tomorrow is a very good time to ask them at the Ask the Trainer, so that we can, see some of these potential solutions, to see how much can be done using Classic and how much potentially can be done using nodes. And the answer is yes, you can modify meshes using splines. And yeah, anyway, let's see what a couple of questions I think for you. Let's see. This is the one that Donovan replied. Core 4D has a series of very basic workflows and so forth. The other thing that Donovan has brought up many times, and he's right, there is type of workflow in Nodes which doesn't require you to understand data structures and all that. That's the modeling component of Nodes. You can string together many node setups.
That's what we're doing next time.
Yeah, you're going to show that, aren't you? Okay, so
next time we will doing nodes modeling. So there's not
there you go. So that's
technical stuff that will be a bit easier. So to follow along, hopefully.
Fantastic. The other one which we get very often, Lisa says, what GPU do you use on your system? You seem to handle your files very well in your system.
It's actually, I have a very old GPU here. I have two of them. I have 1080 Ti here in my computer, so not even an RTX card or something.
Yep.
But yeah, it's because nodes mostly work on CPU.
Yep.
My CPU is, I think it's a Ryzen. I don't know. It's an AMD thing. Not totally true, but nodes is, I think, also good CPU is the important stuff, not the GPU.
Yeah. Well, my system is at least 5, maybe more, older. Dell workstation with an RTX 5000 with 16 gigs of RAM. So it says it's a bit slower than I think a 2090 or something like that. I'm not absolutely sure, but that will be it. Excellent. Mm-hmm. Yeah, Lisa. Wow. 1080 Ti. Yeah. Excellent. So, okay. What happens, Scott, so to the setup when you have a moving or morphing emitter source and a target that is also moving or morphing?
Yeah, of course you can move this. You can move the emitter as. Oh yeah, it's maybe something that makes sense. Maybe put the emitter into a null here, so we can rotate it around. Here you go. Whoops. Let's go. Okay, let's play. Let's make the particle smaller here, maybe, and a little bit faster. So then you can start to rotate this around and place the particle on the surface.
Yep, and you can move the mesh as well.
Yeah. Oh yeah, and of course, because that's the you see now it's the important part here. When you like to move the object around, so that's why we made this here. So when you import a geometry, transform it first with the matrix. So otherwise, maybe you can see what will happen when we change this here. So let's plug in this directly. Let's press play again, and now you can see it starts to. Because we have just the raw geometry here, you can see don't take the matrix into account. So
all the projects, you just butt in again for shilling 5 or V. All the projects, you'll find them in the description text below. If you go to in the link in the description, you will find all the projects you just sign up, and the link you're going to get through email is valid for the whole month. You can get all the files from all the shows. Well, we've held on to about 100 people. That is commendable. Great job, Dominik. A few thousand will watch it over the next few days. As usual, there's a lot of interest for this subject. Tomorrow we have the Ask the Trainer. At the same time, I'm recording tutorials, and there's going to be a batch out by the end of the month, and then we're going to have more. Thank you, everyone, for coming. Special thanks to you, Dominik, for giving us, the inside scoop on how you make your amazing stuff. And see you tomorrow for the Ask the Trainer, and next week for part 3 of our series with Dominik. So, take care, everyone. Bye-bye, Dominik.
Bye-bye, everybody. Bye-bye.